Good morning, good afternoon, and good evening, wherever you are. Thank you for joining. At CIQ, we're focused on powering the next generation of software infrastructure, leveraging the capabilities of cloud, hyperscale, and HPC. From research to the enterprise, our customers rely on us for the ultimate Rocky Linux, Werewolf, and Apptainer support escalation. We provide deep development capabilities and solutions, all delivered in the collaborative spirit of open source.
Welcome, everyone, back to another webinar. How are you, Rose?
I am amazing. I am so excited for today, Zane. This has been like, I feel like we've been holding our breath for months, years now, and now it's just ready to release.
It is very exciting. It's been very hectic the last few days, getting everything ready and making sure that we're prepared. I'm excited to have everybody in to actually finally talk about the real release of Fuzzball.
I know, but I have a little surprise and I want to show you now first before we let anybody else in the room. So hold on a second here, Zane. Hold on. Stay with me. Stay with me. It's going to be totally worth it. Here, can you see me? Come in.
I see it.
Hey, Fuzzball.
There you go. Oh, that's awesome. Very cool.
I'm ready. Release me.
Does your Fuzzball have a name?
What? No, this is Fuzzball. I am the Fuzzball.
So that is
King Fuzzball? Okay. There you go. Queen Fuzzball.
We'll take it. So I know we have Forrest waiting in the back. If we want to bring Forrest in.
Hello, everyone. Can y'all hear me all right?
We can.
Fantastic. Well, good morning,
Forrest.
Webinar. I'm great, Zane. How are you today?
Doing well. It's been an exciting last few days, for sure. I know you've been busy getting some stuff ready to show us, so I'm excited to see that here in a minute. But real quick, just because I feel like we've done this quite a few times, but if you would just give us a quick overview, like what is Fuzzball?
So, yeah, absolutely. Fuzzball is CIQ's platform for the latest in high performance intensive and enterprise computing. Fuzzball is our unification of kind of a lot of different spheres of the computing world right now into one platform that works for everyone's use cases around AI, machine learning, simulation, data analytics, more enterprise type workloads. Fuzzball is the next generation of computing and what we sometimes call HPC 2.0. So it's very exciting.
It is very exciting. We do call it HPC 2.0, and I know we've said that a lot. We talk about it a lot, but what actually makes it the next generation? So why is it different?
So at its core, Fuzzball kind of does away with some of the legacy paradigms and architectures that we've used in high performance computing for a long time, and replaces those with a much more modern architecture that's based around the best practices that have been established by places like cloud, hyperscale, and enterprise. So Fuzzball essentially integrates, for example, tools like Kubernetes and CI/CD platforms, things like that, into a platform that is easy to deploy both on-prem or in the cloud, and allows you to write up, for example, workflows for your users so they can codify the work that they do in computing and run that on the reconfigurable resources available through the Fuzzball platform. So that means AI, machine learning, data analytics, simulation and CFD or finite element analysis. Fuzzball is for all use cases. And as I said, is the integration between Kubernetes and kind of the world of high performance computing that the industry has been looking for a long time. So.
And that's something I want to go back to here in just a second. I want to talk about the Kubernetes specific piece, but I think we have Greg waiting in the back as well. In fact, there he is.
Hi, everybody.
Good afternoon, Greg. Welcome.
It's still morning here, Zane.
That's true. It is still morning. It's not for me, but it's for you. So Forrest was just telling us kind of high level what Fuzzball is, but I want to take a step back and I want to ask you, Greg, why did you start building Fuzzball? What brought this to light? What made you want to go do this?
So I spent a large, very large portion of my career working doing high performance computing. And people that have done that know that, I mean, we've been kind of doing the same thing for the last 30-ish, almost 30 years now. And which isn't necessarily a bad thing. I mean, when something works, right, you don't fix it if it ain't broke. But what we started to see, I think really ever since the advent of containerization in high performance computing, we started seeing kind of a new way of doing things. And we started seeing more and different types of science and research and computing needs being thrown at these high performance computing resources. And as a result of that, like this architecture that we've been using started to show its age a little bit. It became, it was a little, long in the tooth. And how do we start moving this towards a more modern infrastructure? So that was one side of it. The other side of it was we started seeing more people in enterprise being interested in something called performance intensive computing. And when they're looking at performance intensive computing workloads, they're looking at things like AI, ML, and compute and data driven analytics and so on and so forth. And they're looking at this in terms of, well, what kind of an infrastructure do we need to run this on? And they immediately went to, well, okay, let's look at the cloud infrastructure. Let's look at Kubernetes. Let's look at what everything's offering, everything that's being offered out there today. But historically, enterprise hasn't had this sort of a need before. Like most of the time they're doing services. They're doing like, infrastructure type requirements, which the application requirements of that infrastructure is actually very low. This is why virtualization took off so big in enterprise, because you can have hundreds of VMs running simultaneously on a single server. When you're talking about performance intensive computing, you can't do that. You really need to be focused on how do you most efficiently just how do you run your applications? And if you're trying to run 100 at a time, you're not going to run them efficiently. So how do you start thinking about this in a different way? Now, I went to countless meetings at various enterprise organizations about 4 or 5 years ago now, who basically outlined to me they've got an HPC problem to solve. And as I looked at what they're trying to solve, the answer was clear to me. Go build a Beowulf. This is what you need to build. And their response is, oh my gosh, I remember those architectures back when I was a student in the the late 80s. Certainly there's a more newer way of doing this that's more in alignment with how what you want us to use SSH? We're trying to stop using SSH. Now you want our users running SSH and logging in, getting actual shells. They don't know how to use Linux. I mean, this was the kind of responses we would get. And so enterprise really started going to the tools that they know, which are things like Kubernetes. And Kubernetes is great for microservice. It's a fantastic microservice platform. I have yet to see an extremely compelling HPC use case using Kubernetes. It'll come, I'm sure. Someone, it'll get there. I don't believe it's there yet, and I believe that it's the expression putting a saddle on a cow. It's kind of what it reminds me of. And I found some cool pictures. I actually asked some AIs to actually draw me some pictures of saddles on cows. It was pretty cool.
Where, Greg? Where is this?
Forrest, that could be one of our next webinars, maybe a demo. We did this in the past a while ago.
We'll see what we'll put together.
But to me, that's kind of like what doing a high performance computing on Kubernetes is like. It's just not designed for it. It's fantastic at what it's designed for. Just that's not what it's designed for. So could you do it? Yeah, maybe. I don't think it's been done yet though. So when we started looking at how do we modernize high performance computing, we really took the best of all the different industries, the best capabilities, the best technologies, and ideologies, and put them together into a unified solution that we call Fuzzball. And Rose, I love the hat. That is so cool. You remember those in the 80s, the ones that are on the pencils and you can spin them real fast?
Absolutely.
Can you do that?
You know, I actually have a turning chair, but I don't know if it's real fast.
That's awesome. That is awesome. So we started pulling the best of all these different sectors of these different technologies within the ecosystems, and that's where we ended up with Fuzzball. It is a cloud native, on-prem hybrid computing solution. The infrastructure of it sits on top of Kubernetes because that is a microservice platform, and Fuzzball Orchestrate is a microservice solution. And but when we do the compute, we do it outside of Kubernetes because we wanted to make sure that we're getting the most efficient use of that hardware. And Kubernetes hasn't proven to be extremely lightweight at this point. So it would typically get in the way of when really running a lot of performance intensive computing. And so we can build this whole thing up and literally create a service for performance intensive computing. And this isn't our idea. I've now seen Gardner and other analysts actually talking about performance intensive computing as a service, or PICAS for short. And that's just awesome.
Is it?
I'm sorry. Whoever came up with that acronym really.
I was kind of wondering about that one, guys.
I saw PICAAS and I was like, you gotta be kidding me.
It's more like a Picasso, like a Picasso.
Oh, Picasso.
That's in my mind. That's where I was going with it.
It just sounds like you're saying PICAS really elegantly.
I just like how the number of letters that you're allowed to put in front of the as a service there is gradually growing as the years go by. It used to just be a software. Now we're up to a full 3 characters there. What next? Very cool.
So that's what Fuzzball really is, and that's why one of the reasons why I started thinking about this. And the last thing I'll just mention on this thread, and then I promise I'll shut up for at least a minute or two, is the topper on the cake. And some people may have seen some of my other talks and whatnot, know this story, but I was hearing enterprises say they need something more modern. They need something that can do more than just a traditional HPC. And honestly, I was still kind of like, I got my blinders on. This is the right solution. You all are just, too cool for this. But yeah. Then a big, huge social media company called me in and said, we're going to be the biggest HPC system in the world. Here's how we want to do it. And they described an architecture to me that literally just I've never heard of and I never considered. And it was so massive. It was so big that honestly, it was so cool that it really just kind of put my brain into overdrive. And I joke around about going completely OCD, thinking about how to actually solve this problem. So started thinking about this. This social media company, we even talked about, me working there and me helping them build this, but I actually thought it would be much more interesting to go and build this as a company and offer this back to the world as a solution. And that's what we did. And thus CIQ was born.
Thank you, Greg.
Fantastic.
Thank you for that. I think all of us working at CIQ is happy that it exists and it is happening. So appreciate that.
Absolutely. And it looks like we have somebody from Mexico City watching. Linnea, appreciate it. Thank you very much for watching. Welcome. You both have mentioned Kubernetes in this, and I think that was an important distinction. I thank you for diving into that, Greg, and calling out where Kubernetes sits in this, and that it's not running the actual compute, it's running the orchestration piece of this. And it's actually, once you get off to do the compute, it's different. So thank you for clarifying that. Forrest, I know you brought some things for us to look at. I would love for you to show us. I feel like we've done some of these over time, but the catalog just keeps getting bigger and bigger of the stuff that you had to show.
It does. Give me just a moment.
So while Forrest is bringing this up, and Forrest, don't just talk over me as soon as you're ready. But I want to stress, like this is not just yet another Beowulf. We have completely re-architected the structure of a high-performance computing system and created what we jokingly call HPC 2.0. This really is an entirely new generation of how to think about workload management, workflows, how to think about orchestration, and potentially even orchestration at a much wider scale than what we've been thinking about it. So I'm going to be quiet now that Forrest is ready.
All right, yeah, everyone. So this is the main Fuzzball graphical user interface. So we're just going to kind of go through a couple of quick demos of what some workflows look like in this. One of the big, as we've kind of discussed, concepts in Fuzzball is the ability of users to be able to write workflows that codify end-to-end their computational pipelines that they can then go and take and run through Fuzzball on whatever heterogeneous architectures they happen to have for their underlying compute resources. So this is the main Fuzzball GUI. This is what a user in Fuzzball would see when they hop onto the system. I've gone and done a standard Google SSO login flow before this. So just logging in with my just standard company email and everything. We have a couple of different things in this that are kind of worth showing off real quick. These definitions over here are compute definitions that we have available for the Fuzzball cluster. What we're looking at here is a deployment of Fuzzball running up on AWS EKS. So obviously most cloud providers have some type of dedicated Kubernetes service. That one's AWS's. When we deploy Fuzzball out onto that, we can leverage obviously those engines that are out there on those public clouds. So this is based on AWS EKS. The instances that we're going to be provisioning in this demo are different types of AWS instances that we've set up. So for example, we can use some large CPU-only instances here that are these C5n.9x large types. We have enabled EFA, placement groups, stuff like that for optimal MPI on this type of thing. We can also do GPU-based instances. So in this case, we've got a P3.2x large, and so on and so forth. Over here, we can define secrets and users. Those, I'm going to more so get to the workflow side of things, but this is secrets that you can define within the cluster that essentially allow you to template out on the server side different credentials, things like that, so you don't have to keep those in your workflows. So it adds security. And then users is just essentially the list of users on the cluster, members, owners, that type of thing. Let's see here. So I'm going to go ahead and run a couple workflows. This is what they look like in the Fuzzball system. You can see I have my whole list of workflows that I've previously run here. But we're going to start here in the workflow editor and just go ahead and open a few different use cases, run them, and we'll see how it goes. The first one that we're going to look at is a pretty simple, pretty basic one. This one is GROMACS, computational molecular dynamics, done for pharmaceutical drug discovery, all kinds of different things. In Fuzzball, as I said, users can codify their workflows from end to end, so data movements, image pulls, things like that. Because Fuzzball is based on Kubernetes, everything is done out of container images. So each one of these jobs is a separate container image, and Fuzzball will end-to-end orchestrate the execution of this workflow on those resources that we saw defined over here, based on what I've told this workflow that it needs to go out and run on. So first off, we can define the concept of a data volume in Fuzzball. So in this case, we have a volume here that's going to reach out to this link on the internet and pull down this file, drop it into our data volume at the top level directory with that name. And jobs will then be able to mount that volume. You can see the volume name at that path. So that, for example, in this first job, we can untar that tarball that we pulled down over here in this ingress that's got our benchmark data in it. So that's data movement in. You can see we have all these jobs that do different things. This one's pretty simple, just an untar job. You can see that we're pulling from a container registry here. This is kind of one that we use for different testing, different kind of workflows, that type of thing. So in this case, we have this container, GROMACS C3R, with this tag, Aptainer stable on it. We're going to reach out to it and use essentially a service account type tooling to get into it. One big thing about Fuzzball is how well it integrates with CI/CD systems. So you can see that we can use secrets and credentials, service accounts, that type of thing, to make it very seamless for, in this case, me to just utilize this secret and be able to pull that container into all these workflows as I need, or into all these workflow jobs as I need. Over here, we have resources. So 1 core, 1 GB of memory. This one's a pretty basic job. If we want to look at one that's a little bit more complex, this one right here is doing about the same thing as this previous one, mounting that volume, pulling the same container. But we're going to use 2 cores, 14 GB of memory, and 1 NVIDIA GPU. So this is going to map to a G4DN.X large instance on AWS. So a simple GPU instance, but we get the idea that we're running on a GPU. Fuzzball also supports common paradigms in HPC, like multi-node workflows through MPI or task arrays, also called embarrassingly parallel workflows. In this case, we're running an MPI workflow through OpenMPI. We're going to use 2 nodes, and this is the actual run benchmark step of this. So we're going to go ahead and pull basically the same resources that we pulled for this, but we're going to get 2 nodes, each with these resources on it. Fuzzball is going to wire those together up in the cloud, and then allow this compute work to proceed on those instances. As noted, the Fuzzball Orchestrate stack is run as microservices through Kubernetes. So we're not actually doing the batch compute work inside of Kubernetes pods here, which has significant performance benefits and is one of the big kind of best practices that Fuzzball leverages for how it uses Kubernetes. And then this final job is just catting the logs. So we'll go ahead and run this. We can add a name if we want, demo. Go ahead and start this workflow, and you'll see that we have a success. Workflow started successfully. We can go to the status of that. And this is what the actual workflow kind of interface looks like as a workflow is running. So you can see we have all the steps. This is our definition, what that looked like in YAML. Fuzzball workflows can be written in YAML as well if you prefer to just type them out as opposed to using the interactive editor. So all of that, everything that we just saw in that graphical interface is encoded within this YAML definition here as well. And you can see that we're executing on the different parts of that workflow. We're creating the volume, we're pulling the image, and we're starting on a file transfer in from the internet. So here in a little bit, these will start to run. While we're waiting, we're actually going to let this untar one run really quickly so we can see that go on. And then we're going to, we can talk in the background if we need to while these run, but I'm going to kick off a few more, and we're going to just kind of check back into them throughout the webinar here. So you can see that untar has started. This is essentially reached out to AWS with those resource requirements that I gave it, that 1 core and 1 GB of memory. It spun up a very minimal instance for that and has landed the container on that, landed the command, all that on it, run it, and there's no logs from tar, but we now have that data in there untarred. In just a moment, on one of these longer running jobs, I'll grab a terminal into one of these, and we'll be able to actually kind of look around, see that data, see what's up. But that untar one finishes very quickly. So once that comes up, we'll take a look in there. But in the meantime, we're going to go ahead and kick off a couple more of these really quickly. But we take a look at a little bit of sequencing. So as I said, Fuzzball works for a lot of different workflows. This is some sequencing, genomic sequencing using a common HT-seq star SAM tools type pipeline in genomics. So this is doing a lot of the similar stuff that we just saw in that last one. But this introduces the concept of S3 ingress in Fuzzball. So Fuzzball can reach out to any S3 API compliant object storage and be able to pull down data from that. So in this case, you can see I've got my key and my key ID here that I've generated from AWS's authentication type panel. I've got my region, and then if I wanted to use a different, this by default targets AWS S3, but if you wanted to use a different S3 compliant object storage endpoint, you could put it in there. There's a couple different services, different things that offer that, so it's compatible there. And you can see we're doing 2 ingresses. One is a file of FASTQ input files, so like little genomic reads, like base pair data. And then this is a genome that we're pulling down to compare those two. You'll notice we also have an egress here. An egress essentially allows us to move data back out of this job once it's done. So we have 2 egresses here. One is going to reach into this data volume and pull out the file at results/output and upload it to our bucket into this bucket name, and then those kind of subdirectories in it. We have another one that we're also moving. These htc count.txt and then htc count demo1.txt. So we've got obviously a couple different egresses going on there. So a couple different results files we want to preserve from this workflow. We're pulling down, once again, another container from our registry. It's worth noting that Fuzzball supports not only just private registries, obviously, but any public registry, and for that matter, any private registry. So you can pull down from Docker Hub, you can pull down from the NVIDIA any number of given private registry solutions, et cetera, et cetera. And I'll show you guys that in a bit. The rest of this workflow is kind of what we've seen before, different commands. In this case, we're running some Python scripts inside of this to do a little bit of multiprocessing. And at the end, we're going to wrap up our results into a table. So we'll go ahead and start this. Let's see here. We'll check back in on GrowMax really quickly. Oh, and we can see that this, our second job here, prepare benchmark data, is finished. In Fuzzball, you can set up, obviously, as you kind of saw here, this directed acyclic graph of job dependencies. A better one kind of shows off a little bit more of a complex field here, but in Fuzzball, you can set up, for example, this requires field. So this job will only run after this one is done, and you can set up, pipeline or workflows of execution there. If we go into this run benchmark, we can see that this is printing us out some logs. But furthermore, we can get a terminal directly into the instance running this. So if we go ahead and do, say, NVIDIA SMI, because we're using a GPU, you can see that we've got our NVIDIA SMI output here. We've got 34% GPU usage, 343 megabytes of memory. We don't see the exact process name because of how namespacing works between containers and the host in this case, but it is indeed running. So we've got NVIDIA SMI we can look at. We can check top. So for example, we've got that GMX MPI running on the cores of this instance that we're on. So you can see GMX MPI going there. We can also do things like ls/data because we attach that data volume to this workflow at /data, or just workflow job run benchmark at /data. So we can do ls/data, and you'll see that tarball and the unpacked tarball that we set up in some of our previous jobs. And so yeah, so that runs. We can view our logs. That's kind of interesting. You can see those are running there. We can go back in here and look at this going. And yeah, Fuzzball has support for not only just multi-node paradigms in MPI, but also PGAS networks through GasNet. So for example, you can run the Chapel programming language on Fuzzball and do workflows with that type of thing. Just to point out, if you want to, for example, edit the YAML directly in your workflow screen, you can do so. You can directly type into that if you want to edit something there. What was that I heard earlier about cows on a saddle or something like, or a saddle on a cow, something like that?
Saddle on a cow.
Let's see here. Fuzzball is obviously for all use cases, including the latest in generative AI, data analytics, all that type of thing. So let's see here. A saddle on a cow. Oil painting. Somebody was right. We have done this similarly before, but we did it with Dolly Mini back in the day. So this is genuine stable diffusion running on Fuzzball. Here in just a little bit, we'll be able to kind of see a little bit more about this. But for example, we're pulling down our checkpoint file here for our weights, test image, and then once we're done with this, we're going to upload our generated images back to our S3 bucket that we've been kind of working with before. And once our results are in these, we'll be able to go look at those through that. Yeah, so Fuzzball, obviously for all different types of use cases. It's great for CFD, that type of thing. This is a little bit more complex of a workflow, but I believe we just put a video out on our YouTube channel today that shows this workflow running in action and kind of how the results and stuff come out of that. I'll go ahead and fire it off here, and we'll see if it gets done by the end. We can see it upload live. But we've got, like I said, a great video on our YouTube of this workflow specifically going right now. We see that our Chapel Hello World is finished because it's pretty quick. And we have all of our logs from our 4 locales, because I believe this is a, 4-node workflow. So you can see we have all of, so you can see we have all of our logs, for example, there. As I said, it also supports embarrassingly parallel workflows. I am not a Dask programmer, so this is a little bit of a rough script, but we should get results and everything here as expected. We can obviously do task arrays and things like that, embarrassingly parallel workflows in Fuzzball. So if you've got 10,000 input files and you want to be able to process them all at once, we can set this up so we have 12 jobs that are going to be done here on 3 instances at once. So we can tell Fuzzball to spin up 3 instances matching these resource specifications here. And then we'll start iterating through these files. This script kind of uses an FB task ID here, sort of like what you might expect with like Swarm or something similar, to map these tasks around. But in this case, yeah, we'll spin up 3 instances matching these resource requirements, and then we'll start executing 12 tasks on them. So we'll go ahead and start this up. Yeah, so these are going. And we are kind of just waiting at this point for these to finish. Some of these will take a little bit, but we actually I do have one more. So as I mentioned, in Fuzzball, you can kind of do different types of workflows that maybe are a little bit more complex than just these straight line ones that I've seen. In Fuzzball, on a technical level, workflows in Fuzzball are directed acyclic graphs. So they're essentially a graph that has no cycles and has only one way forward. Like you can't go backwards, basically. And so with that, you can solidly create, like, for example, in this case, this first job, create directories will run. Once that's done, you'll notice that this retrieve query sequence and retrieve database sequences both depend upon this create directories one. So both of those jobs will be spawned once this one is done, and will start running concurrently. Once both of those are done, make blast database will start, and you'll see that it depends on both of those. And then run blast at the very end of this just depends on that. So you can imagine this being a little bit more complex. I don't think I have my much more complex one on hand, unfortunately, but you can imagine this being much more complex. You can kind of extend this out ad infinitum to create arbitrarily complex workflow graphs of, whatever complex data processing with tons of different steps that you're having to do normally on your HPC resources. So yeah, we can see that this GROMAX is finished here. So if we go back and look kind of through this, we can see this is all finished execution. We've got our logs here. I always get a little nervous because GROMAX has some cheeky little quote that it shares that I always get concerned is going to be a little bit too much, but that I don't want to get rid of because it seems like it's like the GROMAX community values seeing the quote. So I keep it around. But yeah, so you can see we have our GROMAX results. We've got our quote. We've got our nanoseconds per day performance. If we cat our full log file, you can see that we've got everything here kind of showing our SIMD instructions, GPU support. As I kind of scroll through here, running on 2 nodes with total 4 cores, 4 processing units, 2 compatible GPUs. So kind of just our standard GROMAX results that we would expect. We then get down here to the bottom, our megaflops accounting, load balancing, and then obviously there's our results. So if we want to preserve this file, we could upload it out to S3. I don't in this case, just because it's not terribly useful. But these are running, and yeah, we can go back and view previous workflows. So these are all, you'll notice I've been running these for a little bit, making sure things are in order. But if we go look at, for example, any one of these past ones, like, actually, let me scroll through these really quickly. Where's that one? Let's see here. You can see kind of what the interface looks like for finished, failed, or canceled workflows. A couple days ago, I was working on getting the HPL LinPack benchmark working on Fuzzball. So for example, I can go back and retrieve this workflow that I ran a couple of days ago. This was 5/16, so 2 days ago. I can go retrieve my logs from it. I can do whatever I want here. I can go ahead and rerun this directly from that. And if we go back to our workflows thing, you can see we now have that workflow running here again. So yeah, those are that's the Fuzzball. Oh, there is one more thing we can look at, or another thing here. Fuzzball isn't just for batch computing, it's also for interactive computing. So in this case, we're going to do a simple Jupyter Notebook type thing. Basically bringing up a Jupyter Notebook, being able to connect to it from our terminal here. Normally, as we've discussed, you'd have to SSH into a cluster. Kind of, this is a little bit of a, a headache of a process to get connected to one of these. You'll see how in Fuzzball, I'm able to port forward this Jupyter Notebook server running out on cloud resources directly back to my user terminal here. And how I'm able to just interact with that without having to directly SSH to the cluster just through my own web browser. So in Fuzzball, to support that, we have the concept of an isolated network namespace. So I can tick this back and forth, and it'll create essentially kind of like a network for this container that I can connect to. And then we're just going to port forward this port back to my local. We're running this on a GPU. We're going to kind of see a few AI use cases in this. So we'll go ahead and run that. And just to point out, I don't think I made it explicit. This blast one, which we can now see is finished, and we can the logs from that one. Logs from that one, which one has logs? There we go. So we can see the logs from our blast workflow here. This is obviously NCBI blast doing genomic mapping. And just to point out, the container we're using in this case is directly something pulled from Docker. So this is just NCBI blast directly from there. We can also do things like, this is lamps, I believe, pulled directly from the NVIDIA NGC as well. We can go ahead and probably run this. I might hold off on this one for a moment, just until these finish. So yeah, so our star sequencing is done. We'll go look at that in a moment. I'm going to fire this one off. So yeah, you can see that we're pulling, like I said, in this case, a Docker image down from the NVIDIA NGC. And then we're going to land this just on a simple CPU node because we're just running this on CPU. Our GROMAX one was on GPU, but this one, just to show you some CPU-only stuff. As I noted, just to point this out, we have this star sequencing that's done. Just lost my windows. There we go. And as I mentioned, this one has some output that comes from it. Let's see here. I need to do. Oh, whoops. Hold on one moment. I have to pull up a different bucket and don't want to yell too much.
Now that we're on camera again, I was reminded to sit up straight and look professional.
Let's see here.
Surprise, you're live.
Yeah, my apologies for this transition. Here we go. Let's get back to this.
Rose, that has got to be the next conference like swag or something we give out.
I like that idea.
I agree. I don't think Robert would agree, but I agree.
You know, I just want to see Robert wearing that.
Oh, me too.
That would be great.
I'll send him one.
Awesome, guys. Yeah. So here on the interface, like I said, I had to go open up an additional directory in the same bucket that we're in here. You can see that we've got, for example, this htc count demo.txt and star results demo.txt here that have been uploaded here today. I don't think there's anything particularly interesting in this file, but you can see this is our like htseq results here. So you can see that from where's that? From the star sequencing here, this egress that we had, that's represented here, but that we defined in this volume right here. We've gone ahead and to this CIQ MISC support demo output bucket, uploaded those couple of files, the HTC count demo 1 and then star results demo 1. So looking at these, we can see that these are all starting to finish out. This task array one, I believe I missed the tasks themselves because I was off explaining other things, but in this case, this is kind of like a fintech type thing. This is running some wrapper scripts. They're just doing kind of some number munging. It spins up, like I said, 3 different instances. It lands kind of a Python multiprocessing library on them called Dask, and then starts running these different tasks that use this Python script that utilizes Dask to do some multiprocessing on that node. So we've got our 3 nodes. These just rerun this one in the background so I can show this sequentially coming out here in a moment. But you can see we have all these tasks that respond from this, 12. Each one of these has its own set of kind of logs and everything like that. We'll grab one of these, and you can see that each one of these is just grabbing a kind of just a file with like 20,000 numbers in it, doing some averaging. But you can imagine some fintech, Black-Scholes numbers, stuff like that, analyzing, say 100, 200 stocks for back testing, all in, kind of embarrassingly parallel format, or you've got 20,000 input files from your space telescope and you need to process them all sequentially. This workflow right here is a fairly small task array, so it's only got 3 nodes basically that are going to run on it. But you could scale this up to 100, 1,000, 10,000, and have, if you've got 1 million files, you could have 10,000 tasks running at once. It's fairly extensible and, as said, built for scale. So we can see that HPL is finished. So we've got kind of our linear algebra system results here. And obviously, as I mentioned, I ran this workflow for the first time a couple of days ago, and I was able to just rerun it. And now we've got it completed again today here. LAMPS CPU NGC, this is completed. We pull down an input file that's kind of just a common, like the standard hello world input file for LAMPS. And you can see we've got, let's do all of our logs here. I'm not running on a GPU enabled node, so it kind of complains a little bit about not finding CUDA, but you can see we have all of our results, CPU usage, etc., MPI tasks. This is just running on some smaller instances, not the FA enabled ones. So we kind of see that, we've got just 32 cores there. But yeah, if we wanted to scale this up, we could run this out on EFA-enabled instances. We can run this out on, the best, essentially, and best practices that there are for MPI on the cloud and AWS. This right here, we should jump into really quickly. This is the Jupyter Notebook workflow that we've been working on. So you can see this is started, and we've got this link here. But if I go, you can see that if I go to my logs here, and I try to open this, I get this problem loading page. If I stop sharing my screen for a second, I will give you all a quick view of what the other way you can use Fuzzball looks like. So one of the things about Fuzzball is that it's entirely API driven. Obviously, this gives us the great benefits around not SSHing, that type of thing. But it also being API driven means that we can pretty easily wrap most of the actions that a user can take versus a cluster in Fuzzball. We can wrap those in essentially whatever wrapper we want. So we've got our graphical user interface, but we also have this CLI that allows you to do all of the same things that you just saw me do on our GUI, but through a through a CLI-based format. So I can go ahead and do Fuzzball context login. This allows me to log into the cluster context. This is going to open. So I'm trying to find my StreamYard really quickly. There it is. So this opens when we control click that. I get this right here. Where's that?
So this also goes back to a question that George asked earlier, saying that the GUI looks amazing, but do I have to use it? And I think it's kind of what you're alluding to now, Forrest.
Oh, I see what's going on here. My StreamYard is on the same window. Sorry, here we go.
Just don't hit back.
Yeah, no doubt.
To answer your question, George, the GUI is amazing, and it's been fun to watch people who typically don't use GUIs actually start using the GUI, but you do not have to use the GUI to do this. You can actually do this all via command line, like Forrest was talking about, and he alluded to very shortly there. You can do everything via command line if you'd like.
This is, where did this window go? I don't think StreamYard is like giving me the option to open the window that I'm expecting it to give me to open here. So I think, yeah, I'm just going to move on. I'm not sure why that's doing that, but here in just a moment, I'll go ahead and do this SSO flow, and I'm able to, this will complete. There we go. Okay, so like I said, that opens up, you control click this, it opens up just the standard Google SSO, select what Google account you want to log in with. Once we're in here, we can do Fuzzball workflow list, for example, tail 10. And here are all the workflows that we've just been running as a part of this kind of webinar. So there's star sequencing, Chapel Hello World, the Stable Diffusion one, which is finished. Open from Paraview, so there's everything we've been running. We can go ahead and do a Fuzzball, let's see, workflow port forward, if I can type. Grab the ID of the workflow from here, and then the name of the job and the workflow that we want to connect to in the ports. So you can see we've now got this listening on our remote. I'll go ahead and stop screen here, open up this. And where were we at? So back in this window here, you can see we had a problem loading page. But once yes, I am sharing the right window, cool. Once I go ahead and refresh, you can see that we're connected in here as we would expect. So this is, as I said, a Jupyter Notebook instance running out on some cloud resources on AWS. We've got a workspace we can go into here with some notebooks. So this is gonna, for example, this is just AI training with PyTorch. We can go ahead and run through these. We're gonna train a simple model on the CIFAR 10 data set. So we've got our data set downloaded and extracted. Go ahead and show a couple of the images from that data set. So you can see we've got a plane, bird, dog, bird. Go ahead and set up the code for the model itself, and then set up a little bit more code. And then this right here actually starts training this model. So if we go over here, as we might want to in our Jupyter Notebook, we can do a quick NVIDIA SMI, and we can see 28% GPU usage, 947 megabytes of memory. Again, because of namespacing, we don't see the exact process, but we can do top and see Python 3 running there. If we go back over here, we can see our loss values starting to be printed from this training. If we go over here, refresh this. Actually, here, this is what I want. We can also access that same information through here. So you can see we've got that Python 3 there, NVIDIA SMI. Yeah, we can ls, let's see, /workspace. And we've got there are notebooks and everything, as I just showed in the other window. This will finish training here in a little bit. And you can see we've got kind of our 302 and stuff like that coming here from the output of this. So like this right there, some of these different bits of information being captured in the logs. And yeah, once this is trained, we can pretty easily just go right over here, download this directly to our laptop. Once we save right here, the CIFAR network.pytorch file, we'll be able to really easily, let's see here, you might be able to see this, but if I go back over here, you can see we now have CIFARnet.pth, and go ahead and download, and I get my CIFARnet file. I'm not sure if you can see that pop up, but I can go ahead and download it. That goes right to my local. And yeah, this will stay alive for as long as we set the timeout value right here too. So this will stay alive for 30 minutes before it'll close. We can go back over here and check our, this one right here. So Dask, I missed it again. My apologies. Well, you can see our last task here running on this Dask one. So that normally these would spin up and you can kind of see them in action, but I've kind of missed that. Anyway, you can see our last task running there. You can see we've also got, for example, Stable Diffusion is finished. We've gone ahead and uploaded our images. If we go into, I believe, this bucket right here, I should be able to refresh. Yeah, and there we have our blast results from that blast workflow that we ran earlier, and we've got our Stable Diffusion images. So I'll go ahead and download these. And yeah, you can see the only thing that's still running is the AlexNet notebook, because that is set to run just indefinitely for about a half hour. But that everything else we ran here is finished correctly. Dask is once again finished. Lamps is finished. HPL, Blast. Open from Paraview also finished. Awesome. So this is a CFD one. We're doing a whole bunch of different CFD tasks. This, for example, has been uploaded to this S3 bucket, our final photo result. I can just open it. Yeah, I can. There we go. So there's, for example, our crash test image result. You can see a video of this as well on our YouTube channel. So there's that. I believe our stable diffusion images have downloaded. So let me pre-screen those really quickly. I don't see many saddles, but we do indeed have our results as expected. So some cows there. Oil painting like. Yeah, okay, cool. That's about what I have for the demo here today. That is a fairly comprehensive view of what you can do with the Fuzzball system. We've got a lot of different stuff that we're working on, but this is Fuzzball. So
Excellent.
thank you all for watching. My apologies if that was a little long-winded.
Oh, it's good. It's good.
Those are the
It was the fastest full training of Fuzzball I've ever seen.
Thank you. Yeah, that's the long and the short of it right there, everyone.
Excellent. Thank you, Forrest. We do have several questions to get to.
Yeah, absolutely.
Start throwing those up. So Nicholas asks, if Kubernetes doesn't do the compute, why add the overhead of Kubernetes at all instead of just traditional RPM dev install services? It's a great question. Thank you, Nicholas, for that.
So Fuzzball is built out of right now 2 pieces, and there's a third one coming. The base piece is called Substrate. This is what runs on the compute cluster itself. Fuzzball Orchestrate is what orchestrates all the different substrate instances to do all the different things that you saw Forrest just demonstrate. Everything from ingress of data, managing the workflows. And when I say the workflows, it's much more than just what you have in your YAML file. There's a lot of context in that, in the workflow that Fuzzball has to manage. Again, all the ingress, the egress, the volume setup, setting up containers, downloading containers, building the images for those containers, persisting and storing those containers, just to say a few. There's a lot of things that it has to do. Fuzzball itself, or Fuzzball Orchestrate as itself, runs as a microservice platform. So there's a lot of different pieces to it, and they all fit together via microservices. So being that Fuzzball Orchestrate is a microservice or a cloud native platform, it wants to run on some sort of microservice solution. And Kubernetes is just the one that most people are very comfortable with and very familiar with at this point. Also, many of the clouds will offer Kubernetes services. So it's very easy to stand up Fuzzball Orchestrate on top of these various services. So once you have this Fuzzball service running on top of Kubernetes, you can now start running workloads. So one other piece as well is, I believe, Forrest, you ran all of these different workflows in AWS. In AWS, you can kind of think of it as it scales as needed, right? And it'll bring, so every time Forrest would run jobs, it would actually spin up the appropriate number of instances, run those on the right type of instances, and then tear them down when it's all done. If you're running this on-prem, you have a finite number of compute resources. So it will appropriately schedule. We didn't talk about the scheduling features, but it will be able to schedule all of those workflows appropriately for running on an on-prem solution, which again, the scheduling parameters of that is very different than scheduling in the cloud. Hopefully I answered that. Fuzzball Substrate is a traditional RPM dev installed service. Fuzzball Orchestrate is just a lot more complicated.
I like that. It's just a lot more complicated. We'll get into that later. That actually
depends.
True. James, thank you for posting a question here. And he says, are you showing this in the cloud today? And you mentioned hybrid cloud. Will this be a true hybrid cloud platform?
So I just mentioned that there's 2 pieces of Fuzzball that we're showing off today. And there's a third. So there's Substrate at the bottom, Fuzzball Orchestrate, which orchestrates all the different substrates. And then there's Fuzzball Federate, which sits on top of Orchestrate. because, as Forrest mentioned, there's no SSH involved in this. The entire thing is API driven. It makes it very easy now for us to extend Fuzzball clusters and unite them. So to the question, yes, we can actually, absolutely, you can run a Fuzzball orchestrate instance in AWS in one availability zone, a Fuzzball orchestrate instance in a second availability zone, Fuzzball orchestrate instance in a different cloud and on-prem, and then federate them all together. And when you do that level of federation, Fuzzball Federate is going to be making meta orchestration decisions based on things like resource availability, cost, how much does it cost to run? So obviously, if you've got on-prem resources, it may be much cheaper to run than having to go spin up cloud instances. And then lastly, data. Where's that data? And when you look at all of these together, you actually get some really interesting possibilities in terms of scheduling. So as an example, well, it's cheaper to run on-prem, but my data's up in S3. All right, now you just have to start making decisions on when and how is that job going to run. And those decisions are tuned via policies by the organization. So the organization will control that. Today we are releasing Fuzzball Substrate and Fuzzball Orchestrate. Fuzzball Federate, keep an eye out. It's coming soon.
I like that. That's a good tease. Oh, another question from James. Awesome. Does Fuzzball know what resources you have available, or are you guessing? Or what if you say, I want this resource and that one, like you were doing, Forrest, but then that resource actually doesn't exist or it's being used?
Forrest, you want to grab that one?
Yeah. Yeah, so Fuzzball does know what resources you have available in the cloud. As I believe I showed at the very start of that, there's definitions that you can set that map to, for example, different instance types out on the cloud provider. So you can set up different compute node definitions, for example, that map to different AWS instance types, like their P3 GPU series, their C5N, like CPU series. You can, like I said, essentially map those to different instance types. On-prem, Fuzzball becomes aware of what resources it has kind of as a part of the bootstrapping and setup process with orchestrate and substrate there. So it kind of is able to programmatically determine what it's aware of, what's out there, what resources are on those nodes, etc. If you say, I want this, but that resource doesn't exist, in the cloud, you will essentially just get a workflow failure that says no sufficient provision definitions exist. And you'll have to head to your sysadmin and get a definition put to that. So that's just if like your system doesn't have a matching resource defined in it. If it does have a matching resource defined, it's, as Greg mentioned, going to just reach right out to the cloud provider, provision that instance type live, and then route it back to the workflow to use the compute resources for that. On-prem, it essentially does the same thing. It takes some of the compute resources that are available and assigns them to the workflow. But yeah, so Fuzzball is aware of what you have available. You can define that. You can also, it discovers some of that on its own. And then if you say, I want this, and it doesn't exist, but it knows how to find it, it'll go spin it up or like get some of it. But if it doesn't exist and you don't have it defined, you just get an error, as you would expect. Get some different nodes working.
Thank you, Forrest. So I think that kind of leads into the next question from Sylvie. Yeah, what is the overhead like on this? Since you're actually putting something on each compute node, what is the overhead like?
So this goes back to, I guess Forrest and I are tag teaming. I'll take this one.
That'll work.
Jump in if there's anything else you want to add. It kind of goes back to one of the earlier questions about Kubernetes versus, why use Kubernetes and versus not. So a lot of people that are trying to solve these problems are actually trying to go the other direction, where they're basically saying, we know what Kubernetes is like. We know how that operates. Let's just go run everything in Kubernetes. A lot of the feedback we got is Kubernetes is just way too much overhead, and you're not getting a lot of the performance out of the underlying resource due to Kubernetes just getting in the way. It's just too big. So we spent a lot of effort, and this is why Fuzzball Orchestrate sits on Kubernetes while Fuzzball Substrate does not. Fuzzball Substrate takes a lot of the experience that we gleaned from open source applications like Singularity and Aptainer, and and knows how to run these containers and know how to run this infrastructure in a way that gets out of the way and gives you direct access to that underlying resource in as the most efficient way as absolutely possible. So we have benchmarked Fuzzball in a variety of different ways at this point, and we are getting bare metal speed always.
Great
Yeah,
answer, Greg. Thank you.
really quickly, I know we're very close to time, but just to elaborate a bit on that, we've, just to put some numbers on kind of performance and overhead, we've run benchmarks on some Fuzzball clusters like HPLAI. We've found that we've got the numbers out of those that we've been told by different manufacturer, that type of thing, in that case, that we should get out of that benchmark. So we've seen that Fuzzball provably doesn't add overhead to your HPC. We've also run up in the cloud comparing, doing kind of benchmarks around GROMAX, comparing to some of the numbers AWS has published, and we are dead on to what's out there. So this is, as we've noted, this adds no performance overhead, and like a more standard Kubernetes installation does. And we've got numbers that we've had to back that our overhead is minimal.
Appreciate that. Thank you, Forrest. Oh, Ian, what's up, Ian? Thanks for watching. Okay, so I know that we are like at time of like how we usually do, about an hour, but this is really exciting. This is our release that we've been working on for years. And so we're going to stay on and answer a few more questions. Okay, Ian, for those who are familiar with workflow solutions for the life sciences, for example, Cromwell, I'm not going to read that there, blah, blah, blah. Is there any possibility of a brief comparison or contrast to better appreciate Fuzzball other than just the name? Thank you, Ian. It is a cool name.
Forrest, you want to take it or you want me to?
My understanding around GATK and like Nextflow, things like that, are that those are mostly workflow description languages that give you a very robust way to codify a workflow. But Fuzzball includes a massive software platform backend that actually goes ahead and doesn't just provide a workflow engine, which is one of the microservices that's a part of the Fuzzball Orchestrate stack. There's a workflow engine that takes in users' workflows, parses them out, sends the information to the different parts of the other microservices that it needs to be in. So overall, I would say the biggest difference is that Fuzzball versus like Nextflow, that type of thing, Fuzzball is not just a workflow description language. It's an entire Kubernetes-based platform that you can deploy itself as a cluster, not just take like workflows and run it versus existing resources. Fuzzball is its own entire computing platform that a workflow engine like that is just one component of.
The other thing I would just mention as well is there's nothing stopping you. As a matter of fact, it's encouraged to use those workflow managers inside of Fuzzball. So you can absolutely use that. You can provision out your resources with Fuzzball and then leverage all of those same tooling that you're already familiar with.
I've done things like, for example, taken existing Nextflow workflows and converted them fairly simply over into Fuzzball workflow formats as well. So it's all kind of translatable fairly easily.
We can also, in theory, Nextflow is a little specific as well because it can actually spin up cloud resources and interact with clouds. So we've actually brainstormed in terms of, can we leverage Nextflow as a Fuzzball client? And so that may also come in the future.
Very interesting.
Theory, we haven't actually done it yet. So theory, it should work. By the way, hey, Ian, great to see you. Well, kind of.
So here's a good question that Nicholas asks. Will Fuzzball be free, open source with the option for paid support like Slurm? We get this one a lot. I'll let Greg answer that one.
Yeah, so it is our intention to open source Fuzzball, but we're not going to open source it on day one. We put a lot of research into this, a lot of work into this. And to be blunt, some of the feedback that we got from some of the other companies in HPC is, we're looking forward for you to open source this so we can go and run this and sell it to our customers, again, with not including us. So we are not open sourcing it simply because we want to encourage good behavior and good partnerships with our wonderful partners. So that's our initial goal. As a purchaser of this, we've got no issue whatsoever with providing source code if that's something that you're interested in. Be happy to provide source code licenses.
Thank you, Greg.
Ian's back. Okay. Enough of that. Thank you. I'm getting a great sense from the excellent UI. Yes, it is. But I'm gapping on the execution and overall architecture other than use of containers from any repo.
Yeah, there's a lot in terms of the amount of architecture that we built into this. So again, it starts at Substrate, working up from there. Substrate is a container runtime. Even though we took and leveraged a lot of the knowledge we had from Singularity and Aptainer, we didn't use any of that code, actually. It is a complete new container runtime, specifically about and leveraging APIs to control it completely. So it is an API-based container runtime. That API uses something around the idea of leasing. So you can make a request to Substrate. I'm interested in this 8 GPUs, 24 cores, this much memory, and it's so on, this architecture, and so on and so forth. And Substrate will say, I have that available. Here's a lease I can provide, and so on and so forth. Now, Orchestrate will manage all of the Substrate instances for you. So as workflows come in, Orchestrate will know what each one of the Substrate instances are doing. But at the end of the day, each Substrate instance itself is the source of truth. So it will confirm and check, and then it builds a graph of all of the different places that all these different workflows can run. It breaks apart the workflows and then runs everything on that platform. Again, it also does data management. So it'll do pulling in data, volume management, managing the volume. It runs on parallel storage as well as straight NFS, as well as local. Different types of volumes we can manage and we can build. Does all of that embedded into the platform. So it is an incredibly robust compute and orchestration platform specifically for performance-intensive computing as a service.
Thank you. We have more. Keep going. So Nicholas asked again, what kind of metrics are available to admins? So he's looking for something like Xmod from Slurm. What do we have in Fuzzball?
Horace, you want that one or you want me to?
The metrics backend side of it is, the latest status of that is a little bit more of an engineering question. I know that we have, for example, wired up our Fuzzball installs to Grafana and different common logging tools like that. And we've been able to go in and see how the cluster is running on EKS, all that stuff. So the best thing I can say here is that it works with, for example, logging platforms like Grafana to ingest the logs from a Fuzzball cluster and put those into a searchable format. Greg, I don't know if you have anything to add there.
Yeah, I would just say as well from the administrative side, it's using Kubernetes. It's using a more traditional enterprise stack on the Orchestrate side. So all of the typical tooling that you have for monitoring a Kubernetes cluster, you can use on the Orchestrate side. On the Substrate side, we're as close to bare metal as absolutely possible. And in that side, you could just use Fuzzball in terms of what it is providing, which, to be clear, it's not a huge amount today. It's enough that you can get by. You can figure out what everything's happening and whatnot, but you can't do kind of high-level profiling or real-time metrics or analysis on what jobs are doing through that. If you wanted to do that, there's a variety of solutions you can use, as you mentioned. Really, it's just then a matter of just tallying that data back up and how do you want to present that back to the users. But yeah, Fuzzball is very, very flexible with regards to that.
Okay. Hey, are you guys going to, how do you pronounce this? ISIC?
Just
ISC?
ISC. Yeah.
ISC? What is that?
So the International Supercomputing Conference. So it's the Europe version of supercomputing in a nutshell. Fantastic conference. I'm not planning on going, and I think we are sending some people. But yeah, we're still figuring that out. There will be at least several of us over there. We're a pretty big company at this point. Well, big, right? I guess it's all relative. For me, it's a pretty big company. And we're at about 85 people right now. So, and we are international. So, we do have a number of people in Europe. So we'll probably send some people from the United States over, as well as have some of our European contingent join us over there. So yes, but not me.
I have maybe a silly question, Greg. Does Fuzzball really take away the need to have a head node? Is that?
Yep.
Can we just get rid of that? Is that gone now?
Yeah, it's complete. It is gone in a traditional sense. So what Rose is asking is, in a traditional Beowulf architecture, we typically see things like you have a control node sitting up on top, and you've got all of these compute or sub nodes sitting below. That control node acts as an interactive server where people will SSH into that control node and then do all of their kind of major interactive work, and then interact with the scheduler that will then run the jobs on the compute resource, on all those compute nodes. Fuzzball does not have this same architecture, and this is what I was referring to earlier. Fuzzball is a new way of looking and thinking about high performance computing systems, and there is no kind of control or interactive system as we've had in the past. Now what we have is the notion of APIs, and there's a number of different interfaces and tooling you can use against those APIs, and it turns an HPC system more into a computing appliance, really, just a massive scaled computing appliance. So you're now interacting with this giant computing appliance via these APIs, which again, users don't usually interact with APIs, but they're interacting with the clients that are communicating over these APIs. So you can use a Fuzzball cluster, even no matter wherever it is in the world, via your laptop or via your workstation. And again, just connecting and leveraging these APIs.
So that brings up a question about security, which I imagine, just because I've known you for a little while, that's top of mind, like making sure that I imagine that Fuzzball is more secure, but can you touch on that?
Yeah. So one of the biggest difficulties or challenges with securing a traditional HPC system is the fact that you are allowing, over SSH, over a secure shell, you're allowing people to have full access to that interactive resource up on top, and then to the compute resources when their jobs are running. And it's very hard to validate that a user coming in is in fact the right user, right? To start it off, thinking about passwords as an example, right? A password is something that only you know. Well, that's the hope, right? Only you know that. And then you can use that password to go get access to the system. But what people found is, it's pretty easy to either brute force or hack passwords and get in. So now all of a sudden people are getting in with your private password, but they're hacking it, right? So then we started using one-time passwords or additional, tokens to get in. So multi-factor tokens or multi-factor MFA, multi-factor authentication, to get into these systems. But again, that just kind of solved the problem for a little while. Giving users full access to pretty much do whatever they want is a very difficult thing to secure. Fuzzball, because everything is going through those DSLs that Forrest was showing, those workflows, everything is defined. You can reproduce, you can replay, and you can audit every single action that's happened. As a matter of fact, all of the data ingress and egress could be completely locked down to the point where we're actually getting authentication or authorization for any sort of IO going in or out of the system via another source. So if a lab or classified facility has limitation in terms of where they can pull data from, or who can pull that data, or what applications are allowed to be used against that data, we can integrate that via the ingress and egress. And we can also lock down when the job is running, we take it off the network. So they have to do all of their ingress and egress via that section of the DSL. So we can now start securing these workflows in a way that honestly we just haven't been able to do before. And it gives a lot of capability in terms of management, right? This is the type of thing that a CISO or somebody who's really focused on the security side is going to be very interested in making sure that everything is auditable, it's reproducible, and it's secure, not just secure from a hacker perspective, but secure from a supply chain perspective. Keep in mind, everything that we're running now is also coming out of something that can be verified and validated. Each one of those containers can be validated. So, excuse me. So we can very easily have complete transparency on everything that's happening, and then trust on everything that's happening. So yeah, security is definitely top of mind.
Yeah, thank you for that, Greg. I feel like we've kept you a little bit longer. I think you might have a couple other meetings to go to, but thank you so much for coming on and sharing with us the story and building this amazing company, and releasing Fuzzball and making it fun and awesome. Really appreciate your time being here. And I don't know, Zane, if you have something else to say, but you guys, we are open. We are open for business. We are ready for your comments, your questions. You can go to our website. You can schedule with us and dive a little bit deeper onto how Fuzzball can really benefit your environment and how we can work together. And we'd love to chat with you. So leave a comment, leave a like, say hello, share with your friends, schedule a meeting. We're here for you.
Absolutely. Thank you all for watching. And I want to thank the engineering team. I know you guys have put a lot of time and a lot of effort into this, so we really appreciate it. Forrest, appreciate all the work that you've done. I know you spent a lot of time working on these workflows to be able to show people and show off Fuzzball, and it's been fun watching you over the last almost 2 years now play with this thing and watch it grow. So really appreciate everybody out there. Like Rose said, go like, subscribe. If you want to talk to us more about this, go to the Fuzzball page and sign up and give us some time. Appreciate it. Good to see you guys.